Alright, as promised, I have the second energy video for you. It should be a familiar setup to problems we've seen so far this term. We have a 3 kilogram block starting sliding up a 22-degree incline at 9 meters per second. If the coefficient of friction between the block and the incline is 0.12, how far will the block slide up the ramp before coming to rest? I'm actually going to do this problem 3 separate ways. I'm going to first use F equals ma in the kinematic equations, back from Unit 2. Then I'm going to solve this problem using the work energy theorem. And lastly, I'm going to solve this problem by using conservation of energy with non-conservative work. And the goal of this will be for us to get the same answer all 3 times, no matter which method we use. So to start with, let's do our F equals ma, one we should be fairly well familiar with by now. So we have our incline right here, and as the block slides up it, we have a few different forces that are acting. So those forces are the weight, which acts straight down, the normal force, which is always perpendicular to the surface, and we have the force of friction acting against the direction of motion. So you might notice that we have no forces in the direction of motion, but thankfully we're not required to have a force in the direction of motion, so this will all work out just fine. And we will need a coordinate system, so I'm going to have x be positive up the ramp and y be positive coming directly out of the surface of the ramp or in the direction of the normal force. So most people, or most of you, will be fairly familiar with this approach by now, but the first thing we're going to do is write our F equals ma equations in the x and y directions. From a little bit of experience, the force of friction in the x direction, we have no hope of finding that value without the normal force, so I'm going to do my y direction first. The sum of the forces in the y direction equals the mass times the acceleration in the y direction. And in the y direction, we have the normal force in the positive y and the y component of the weight in the negative y direction, where this is the triangle we'll be using to break the weight down into its y and x components. And this angle up here at the top, that is our 22 degrees. And the acceleration in the y direction is 0, so normal minus the y component of the weight is 0. As a little aside over here, let's just go ahead and calculate the force of weight, which is m times g, which is 3 kilograms times 9.8 meters per second squared. And we find that the weight has a value of 29.4 newtons. The y component of the weight is the adjacent component to the angle we've been given. So the normal force equals the y component of the weight, and the y component of the weight equals the magnitude of the weight, 29.4 newtons, times the cosine of 22 degrees. So we find that the normal force equals 27.3 newtons. And then from there, we can go on to the y direction. I'm going to flip over to red, why not, for the x direction. Same approach in the x direction. Sum of the forces in the x direction equals mass times acceleration in the x direction. We have the force of friction acting in the negative y direction. The negative x direction, my apologies. and the x component of the weight also acting in the negative x direction, and there is an acceleration in the x direction. Since our y acceleration is 0, I'm just going to call our x acceleration a. So to get a value for our force of friction, force of kinetic friction is the coefficient of kinetic friction times the normal force. So that is 0.12 times the normal force, which is 27.3 newtons. And we get a value for our force of friction, which is 3.27 newtons. Now, going back to our F equals ma equation, we have negative 3.27 newtons, 3.27 being the magnitude, the negative specifying the direction, minus, and for the x component of the weight, the x component is the opposite component. So we need the magnitude, 29.4 newtons, and opposite goes with sine, so times sine of 22 degrees, equals ma, which is 3 kilograms, times whatever value we get for a. So working through this math here, we find that the acceleration is negative 4.76 meters per second squared, and we should check to see that the negative makes sense. The block is traveling in the positive x direction, but slowing down. Slowing down means the acceleration is opposite the direction of velocity, or the negative direction. So now to flip to, we'll go to this yellow color for the end of the problem. Now we have an acceleration, and we want to know how far the block has traveled. So we have a is negative 4.76 meters per second squared. Delta x, the distance the block travels, is what we want to know. These are starting to look like variables of motion, which means we're going to need the kinematic equations. We need 3 variables that we know and 1 unknown. So we know the initial velocity is positive 9 meters per second. And we want to know how far the block travels before coming to rest, so Vf equals 0. The equation that relates these variables to each other is Vf squared equals Vi squared plus 2a delta x, or 0 squared equals 9 meters per second quantity squared, plus 2 times negative 4.76 meters per second squared times delta x. And we can solve for delta x, the distance the block travels up the incline, and we get 8.51 meters. So hopefully this doesn't feel like anything new. This is all stuff that we learned in Unit 1 and in Unit 2. Mostly, we just wanted to do the problem a way we already understand so that we can compare our answers to Part B and C to our answer to Part A to make sure that we're getting these same numbers no matter what way we do this. Make myself a little dividing line there. So now we have the work energy theorem. And the work energy theorem states that the net work net, equals the change in kinetic energy. So the change in kinetic energy, the right side of the equation, is relatively easy. That's kinetic energy final, 1/2 mvf squared, minus kinetic energy initial, 1/2 mvi squared. And we already know that Vf is 0, so this whole term right here just becomes 0. Now, what the net work means is we can either use our definition for work, force times distance traveled times cosine of theta, and use the net force, or we can just add up the work done by all of our forces. From our free body diagram, we already know which forces we have. We have the normal force, the force of friction, and the force of weight, which I'm going to label with the subscript mg so that we don't have w subscript w. But if we find the work done by each of these 3 forces and add them all up together, then we will have the work done by the total force, or the work done by the net force, or the net work. The formula in general that we're going to be using for these is that the work is the force times the distance traveled times the cosine of theta, where theta is the angle between the direction of travel and the force. So let's go through these forces one at a time. The normal force would be force times distance times cosine theta. The force is the normal force. The distance we don't know, that's what we're trying to find. D is our unknown. But if we go to our free body diagram over here, to draw something in green that is not a force, not part of my free body diagram, but just to draw it on here, D is going up the ramp that way. So the angle between the normal force and the direction the block is traveling is 90 degrees. Well, the cosine of 90 degrees is 0, so the work done by the normal force is, as usual, 0 joules. To move on to another one that's at least relatively easy, the work done by friction is the force of friction times the distance times cosine of theta. And thankfully, we've already done our work over here in the free body diagram, because otherwise we would need the value for the force of friction here. If we hadn't already done part A, we would have to go do at least this red and this blue part in order to find the force of friction. But thankfully, we have already done that, and we know that the force of friction is 3.27 newtons. We still do not know D. And the angle here, well, look back to our free body diagram. The distance traveled is up the ramp. The friction acts opposite the direction of motion, or down the ramp. So like usual for friction, we're going to have an angle of 180 degrees, and cosine of 180 degrees is -1. So our work done by friction is -3.27 newtons times the distance that we travel. And last but not least, we have the work done by gravity, where we want the force of gravity, or the force of weight, again times the distance, again times the cosine of theta. And plugging in here, we already know the force of weight is 29.4 newtons. Times the distance, times the cosine of, now we need to come up with an angle. So we want the angle between the direction the object is traveling and the force we're talking about. So we want this angle right here that I've labeled in orange or yellow or whatever it looks like to you. So we've got to add up two angles here. We have the 22 degrees inside this weight triangle here, and then we have to add that to the angle between the y component of the weight and the direction we're traveling. Well, we're traveling in the x direction, so that's 90 degrees from the y direction. So here, we will get our angle simply by adding 90 degrees and 22 degrees, which gives us 112 degrees, or the work done by gravity is -11.01 newtons times D. Let's put that negative outside the parentheses there, for no good reason, really. Then we can go back to our original equation and start to plug things in. So by original equation, I mean this one up here that I just circled in red. The work done by the normal force is 0. The work done by friction, dropping my units for the time being, or no, I'll keep my units, 3.27 newtons times D. The work done by gravity is -11.01 newtons. times d equals 1/2 times the mass, 3 kilograms, times the initial velocity squared, so 9 meters per second, that whole quantity squared, and we had minus the initial kinetic energy, so we need a negative on that side. I lost that from before. So once you jam all of this together and beat it a little bit with your math hammer until it gives you the number you want, you find that D equals, again, 8.51 meters. And now on to the last part. So to use conservation of energy with non-conservative work, the equation we start off with is total mechanical energy initial plus or minus the work done by non-conservative forces equals the total mechanical energy final. Now, presumably it's obvious here that my initial point is when the block is traveling 9 meters per second, and my final point is when the block has stopped. But I still do need to define my h equals 0, and I'm going to put that right when the block is starting its motion, when it has that 9 meters per second in the initial case. So now we just need to figure out what kinds of energy we have present. So our total mechanical energy initial, are we moving? Yes, we're moving. So we do have kinetic energy to begin with. There are no springs, so we couldn't possibly have any spring potential energy. And we're at h equals 0, so we do not have any gravitational potential energy. The work non-conservative is just going to be the force non-conservative, whichever non-conservative force we have, times the distance traveled, times the cosine of theta. With the same definition as before, the angle between that force and the direction the object is traveling. Just for anyone who hasn't been in my class before, this plus or minus here is just a reminder. It's letting you know that the work done by non-conservative forces can be positive or it can be negative. And you should know what to expect. If the non-conservative force is taking energy away from the system, we will expect a negative answer here, or a negative non-conservative work. If the non-conservative force is adding energy to the system, we'll expect a positive non-conservative work. But that positive or negative comes from the cosine of theta. You don't need to put it in yourself. Just wait for your cosine of theta term to give you a positive or a negative, but it's good to know what we expect for this positive or negative sign here, because it can allow us to check whether we've got the right angle. Here, friction always works against motion. So friction almost always is taking energy away from our system. So I'm expecting to get a negative sign there. We'll see if I actually do. If not, I've done something wrong. But back to our equation, and then total mechanical energy final. Again, we have no springs, so no spring potential energy. The block has stopped moving, so we have no kinetic energy, but we're no longer at h equals 0, so we will need our, oops, too early for that, gravitational potential energy final. So now we can actually start to plug some numbers in, or plug in equations. So kinetic energy is 1/2 mv squared. Again, actually I'm going to drop the minus for now, but I still know that I'm expecting a negative sign here eventually. Force non-conservative is whichever non-conservative force we have. Here, it's the force of kinetic friction, times the distance the object travels up the incline. So let's go ahead and label this on our diagram. From where the object starts to wherever the object ends. This is our distance d. And then times the cosine of theta, and theta here is going to be 180 degrees. Again, the angle between the direction the object is traveling and the direction of the force itself. Notice that it's the same angle we got when we calculated the work done by friction before. Since friction is our non-conservative force, the work done by friction is the non-conservative work. And this all equals m times g times h final. Now, we don't get to cancel out a mass here. Technically, we could, because the force of friction, if you look back way on the left side here, the force of friction did have the normal force in it. And the normal force was equal to the y component of the weight, and the weight has a mass in there. So technically there's a mass buried somewhere in that FD cosine 180, but we can't see an m, so we can't cancel a mass out. But we can start plugging in numbers. 1/2 times the mass of 3 kilograms times the initial velocity of 9 meters per second, quantity squared. Cosine of 180 is -1. So there's my negative sign that I was expecting. Good, we got a negative sign. The force of friction, again, thankfully we've already calculated the force of friction way back in part A. If we had not already calculated the force of friction, we would need to do some free body diagram stuff to find it. But thankfully we've already done that, so we just know it's 3.27 newtons. And we don't know d yet. Equals the mass, 3 kilograms, times g, 9.8 meters per second squared, times hf. And if you've watched the other video, you might notice we've run into a similar problem. We have two unknowns in this equation. So the only way we're going to be able to solve this equation for the unknown we want, d, is to ask ourselves, are d and hf related? And for this, I'm going to go back up to my diagram at the top. If wherever we started, right here, was h equals 0, then however far we are above that point is going to be our h final. So h final is going to be the vertical component of this triangle, and d is the hypotenuse, where our angle 22 degrees is still down here at the bottom. So using a trig function, we can definitely relate d and hf to each other. The sine of 22 degrees is hf divided by d. Or written a more helpful way, d times the sine of 22 degrees equals hf. So that means we can take this d times sine of 22 degrees and plug it into this other equation in place of hf. Now, all we have for our unknowns is d, so we can just continue on to solve the rest of the problem. And working through this a little bit, for our kinetic energy here at the beginning, we get 121.5 joules minus 3.27 newtons times d equals, so now we want to take 3 times the 9.8 times the sine of 22, and that gives us 11.01, the units being kilograms times meters per second squared, or newtons, times d. So, if this looks a little familiar, take a look back at this last red line in part B. We're more or less to the same identical line in the math, although we took a different approach to get there. But from here, it should be fairly easy for you guys to solve this one and get our final value of d, the distance traveled up the ramp, is 8.51 meters. So we get the same answer, 8.51 meters, no matter which of these three methods we use for this problem. Any of them are acceptable on a test. If I want you to use one method in particular, I will tell you. If I say use energy methods, that means you can use the work energy theorem or conservation of energy, and it's on you to know whether you have non-conservative work or not. But it's at least reassuring that the methods we learned in Unit 1 and Unit 2 are matching with the methods we learned in Unit 3. That's about it for this video. If you haven't seen the other video on just regular old conservation of total mechanical energy, you should go check that out. But this should be helpful for your homework problems and the type of energy problems that I ask on tests. Thanks for watching. Have a good day.